everyone. Welcome to another live session for the OMEX. As always, I hope my voice is clear. Would want you to give me a quick thumbs up if the voice is clear. Okay, thank you. Let me share my screen. So we'll wait for 1 more minute. Let's see if other people are joining us. And then we want to essentially keep this session short and sweet, build a little more depth on what we've been doing so far. And in this 1 minute that we're waiting, let me just recap what we've done. We covered how to calculate the units digit of a power. Yes. Then we covered how to calculate the remainder when an exponential term is divided by another number and see the pattern of the remainders, right? And then we did the binomial theorem, which was being used in the previous thing, calculating the remainder when an exponent is divided by a number. We were using the binomial theorem intrinsically, and that's what we covered yesterday. And then to get into the concept of the last two digits, and at least for those that are ending with 1, those exponents with the base is ending with 1, we discussed yesterday as to how we can use the binomial theorem to crack the last two digits, right? So that's where we are going to build from. So what am I going to cover today? I'm going to try and take the case when instead of 1, that base ends with 9. Let's do that part today. And I'm going to link it with this live NMAT sum that I faced in the mock, right? That I gave right before these sessions, right? So I'm going to now take numbers in which the base ends with 9 vis-a-vis the one we did yesterday, where the base was ending with 1, and then we were able to calculate the last two digits. Today, we're going to end up doing it when the base ends with 9, and slowly, maybe all the other digits as well. And you'll come to know of the myriad techniques we have so as to crack one same sum, right? As we do it for the various digits that are going to come in. So let's look at 9 now, okay? And let me actually go back to the very basic school, sort of a rule that we know, that how to test whether numbers are divisible by 9 and what will be the remainder when a number is divided by 9. So I would like you all to recall and give me a thumbs up that do you all know that, oh, we take out the summation of the digits and then we, sort of keep reducing that to check whether the number is divisible by 9 as well as get to the remainder if not divisible by 9. Are we okay with that part? And I'm sure most of you all know it. Check. Check. Good. Now I'm going to ask you all an important thing. Do you all know the reason why that is true? Right? This is where, so I'm building right from the basic. Why is this test of divisibility by 9 and whatever is left then will be the remainder? Why are these things true? And it's going to utilize a technique which is very good for number property questions. So anyone who knows why these things are true can maybe unmute and talk about it or put it on the chat, or at least give me a yes if you know, or give me a no if you don't know. Right. I would want to know whether you all know the reason behind the divisibility test of 9, and that if it's not divisible, then whatever remains is indeed the remainder as well. Check. And if no, then I'd like you all to put it in the chat that, do we know it? Okay. Or do we not know it? Okay. So now see what I'm going to do. Okay. I'm going to take a random number. Okay. Now see, this next step that I'm going to write is a very nice, important step, a representation of the number with these digits. What does it become? Can you see this? F sort of 10 to the power 0 into F plus 10 to the power 1 into E. What am I utilizing? That our place value system, our base is to the base 10. Everything that we do it in the base 10. And that's what we are utilizing here. So isn't this the expansion? And very important to keep this in your minds whenever you're looking for the sort of the expansion of a number using its digits. This is what it is equal to and can be very, very helpful. Now look at what I'm saying, or what am I going to say? This is F itself. Can I not break this as 9E plus E and then 99D plus D plus 999C plus C? Check. And can you now take it from here? Can you show me aptitude and get to the divisibility rule for 9? How will it be happening? Check. I'm going to isolate now. F plus E plus D plus C plus B plus A. And then can you see from the rest, I can pull out a 9 common. Check. I'm going to wait here for 1 minute. And is it becoming clear what we want to do? Every number can therefore be written as 9 into some integer plus the summation of the digits. And since the rest of it is already always divisible by 9, you only have to check whether the summation of the digits is divisible by 9 to check whether the overall number is also then divisible by 9. Then we can conclude that. Check. And if you followed closely, see, I'm not writing it, but we've basically also done the divisibility rule for 3. Can you see why does it work? That whole summation of digits looks like such a magical thing, but it's very simple. Can you see why does it work here? That with 3 also, the same logic will work out. I'm just going to bring the screen and expand it. Yes. Check. Are we okay? So this is the, let's be clear. What have we done? The divisibility rule for 9. If the summation of digits is divisible, then it is by 9, then the whole number is divisible by 9. And now check. Wouldn't you immediately agree that, let's say it's not divisible by 9, but let's say this leaves a remainder of 2, then wouldn't the division by 9 overall, if the summation of digits leaves a remainder of 2, wouldn't the overall sum as well leave a remainder of 2? So what am I saying? Let's say when you total up the digits and it comes out to be of the form 9L plus 4. So the summation of digit leaves a remainder of 4. So this original number can I not write it like this? And then doesn't it become k dash plus 4? That same remainder will carry forward. So I want you to be clear. Not only is it the divisibility test, it's even more complete. In what sense? That whatever remainder is left after calculating the summation of digits is what will be the remainder for the original entity as well. And that for me, like the complete divisibility rule for 9. Check whether this is okay, right? And give me a thumbs up if it's very clear. And the fact that this also solves or demystifies, so to say, the divisibility rule for 3 as well. Same things work there. Now, one more point here, right? Like you can see the terminology here, digital sum. So digital sum. So can you guess by the way I just said it that what is it that we're going after? When they quote the term digital sum, all they are meaning is the summation of the digits, right? So let's check. If I have 4, 7, the summation is 4 plus 7, 11, which in an ideal world we will sum up again till we get a single digit. 2. So 2 is like the digital sum of 47. Let's say we have 638. I'll give you all one quick 30 seconds to do it and then I'll write it. So do it on your own now. Come on, quick. We have one answer in. Check 9, 17, and therefore 8. Correct. So is the digital sum now clear? Right? And can you see where I want to use it? I'm saying that this thing that you do when you're dividing by 9, you're cracking the digital sum. And therefore, see, the digital sum of a number is also being utilized when you want to either check if it's divisible by 9 or further get the remainder with 9. Okay. So since we're attacking the digit 9 today and overall wanting to get the last two digits, I wanted to take it a step back. First, get the basic thing for 9 clear as to why does this rule, the basic rule of divisibility even work? And it not only gives us divisibility, but even the actual remainder is supplied to us. And the digital sum concept. Are all these things now clear? Right? Great. So now let's first take this sum itself. Can we crack this one? What is the digital sum of 19 raised to 100? Not easy. A novel type of question, so to say. And I'm going to give you all a good 2 minutes. Check. And you all crack this one. 19 raised to 100. The digital sum. What will it be? And although the answers are visible, you don't know whether it's right or wrong, maybe, and still try and get it on your own. Check. If there's a doubt, if you're stuck, I would want you to see what we just did. In fact, let's take these numbers 47. What would you say is the digital sum of 47? And what would you say is the remainder when 47 is divided by 9? Similarly, in 638, what would you say is the digital sum of 638? And what would you say is the remainder when 638 is divided by 9? And then if you see something there, can you try and tame this sum? And what you're going to possibly use is the binomial theorem again. Check. So for 47, digital sum is, and the remainders therefore 2 as well. 638, digital sum is 8. And what we have studied is that itself will be the remainder. So what does it mean? 19 raised to 100 getting its digital sum. And this time we don't know. See, why is it a different sum? Usually we know the digits of a number. So getting the digital sum is easy. And from the digital sum, we go to the remainder. That's how we've always done it in school and all this. That get the digital sum, add the digits up, and then that helps us get the remainder with 9. Here we're going to do something different. The digits are not easily, known to us. 19 raised to 100 is a huge number. You can't do anything there, even if you have a calculator. But if we can crack the remainder when divided by 9, can give you idea about the digital sum. See the backward loop. Now that's aptitude for me. So can you get, by using the binomial theorem, the remainder when 19 raised to 100 is divided by 9? And then if whatever is that remainder is my answer, check. I'm going to again pause for a minute. If you'll need more time, let me know. But no substitute for getting it on your own. Then it's going to stay with you. Okay. Check. What will I break 19 as? And I want you all to punch in your answers if possible. What will you all break 19 as? Will I not break it as 18 plus 1? Because 18 is a multiple of 9 and 1 is very friendly as we saw yesterday. So will this not become 9k plus 1? Very good. Yes. 9k plus 1 raised to 100. And as we saw yesterday, there are how many terms? Let's revise. 101 terms. And 100 of them will contain a 9 in it. So all of them will contain a 9 except for the last term, which is simply 1 raised to 100, which is simply 1. So it's going to leave a remainder of 1. And if the remainder is 1, the digital sum must have also been 1. Check. And see, it's actually come after 30 correct questions, right? So although every time, if you have a string of correct, the next one may not be very tough, and sometimes they break the pattern and an easy one comes. But really on this one, It's come after 30 correct questions. It's a hard one. Gives you great credit when you get it right. And what's at the play here? If someone's just mugged this digital something for 9 only one way, they might not crack it. But if someone knew the proof and was well aware, you can almost there and there in back engineer that, okay, digital sum gives me the remainder might give me the digital sum. And then I'm using my binomial theorem logic as well. And why do these things strike to me? Okay, one you may argue is I've been teaching them, but I feel fundamentally knowing, oh, well, like we derived the binomial theorem yesterday, and today we've derived the divisibility by 9. That is fundamentally helping the mind remember the right things at the right time. Check. Is this sum okay? And now I'll use this sum only because it really doesn't matter which numbers we use. Calculate the last two digits of 19 raised to 100. Check. Hint, we're going to try and use what we did yesterday, which is we know what to do when the number ends with 1, right? So try and trap it in that pattern. And therefore, knowing the first 20, 30 squares is crucial. Can I not write it like this? Which then becomes 361 raised to 50, right? Now, 3 is useless as far as the last two digits are concerned. So this is 61 raised to 50. And then again, for completeness' sake and revision purposes, I'll write it in detail. 50 choose 49 dot 60, right? Raised to 1. 1 raised to 49. Before that, the terms would have 60 squared and even higher powers of 60. So not contributing to the last two digits. 60 raised to 0, 1.50. And what does this become? 50 into 60 plus 1, right? And luckily for us, both digits are 0 plus 1. So the last two digits have come as 0, 1. Check. So yes, I have been able to crack an even power, but do you see one part of the job is done. Any number ending with 9, I can always trap it like this, at least for an even power. Because effectively 19 squared ends with 1. And then I'm going to use, so to say, the tea kettle principle, or, not reinventing the wheel. With 1, I know what's the thing. 6 into 0 was giving me 0 plus 1. Check. And I'm going to now give you another technique and show you the ways in which we can just manipulate binomial theorem and keep getting our answer. So this is, just to play around, build even more strength. Because I know 1 is important, can I not write it like this? Check. And again, I'm involving 1, right? And again, it's a binomial theorem. I just have to look at it as 20 plus minus 1 as my next number, right? So now I'm going to try and skip a few steps. Again, 101 terms, 99 won't matter. Then 100, choose 99, which is 100, into 20, into minus 1 raised to 99, right? Plus minus 1 raised to 100. Check. Now this is minus, so to say 2000, right? And this is plus 1. And as we discussed yesterday, this is still ending with a 0. So imagine you had some crazy number, 98,000 or something, minus 2000. The last two digits are just simply 0 again. Plus 1 is going to lead to 0, 1. Same answer, two methods. One, reusing the digit when a base number ends with 1 and converting it into that fashion. And one, maybe writing it as 20 minus 1. Because 19 is so close to the next tens place, and I can always use this technique. Check. Are we okay so far? If okay, then I'll quickly take the next one, which is 19 raised to an odd number now. And check how will we tame that. But first, quick thumbs up if this is clear. If there's any doubt, good time to ask me. Right? So now 19, let's take a separate thing, maybe raised to 73. How are you going to do it? I want you to try and use M1 again. What can I do? And now try and complete it. And M2, that didn't care, right? Whether the power was odd or even. And now you know, check whether both methods give the same answer. I'm going to give you another 2 minutes. And I want to push as much as possible. Last small topic for the day, right? And we've covered a lot of things about digit 9. And maybe tomorrow we'll take up digits 3, 7, 5, and slowly close in on this topic. You see, we're becoming very strong at it. And then finally, some remainder theorems will come, like the Euler-Totient function and stuff like that. But we're almost now in gear 3 on this topic. Check. Can you get this and give me the answer? Key it in. If you all want me to wait for 2 minutes till you're getting it, I want you all to key that in, because otherwise I'll now start. But I want you all to have the chance, because nothing like getting it on your own. Okay, so let's go ahead with this. Now here I can use the same technique, right? So 19 I can keep out. And this one, which is 361 raised to 36. Same ways I will handle it. Out of the 37 terms, 35 terms are still useless, even though there's an additional multiplier of 19. If the last two digits are 0, then that's that, right? Even multiplying by 19 won't change that fact. So I'm still concerned with just the last two terms, which is 36 into, right? Luckily for this number is also 36. So 36 into 60 into 1 raised to 35 plus simply just 1 raised to 36. Right? This is giving me 1. And this is giving me what as the last digit? It's still giving me 6 as the last digit. Check if this is okay. I'll wait here. And see, the third digit is not important, even if that 19 additionally is there, because that won't affect the last two digits still. So I'm still going for the last two digits of what's inside the bracket, and then we'll use the 19. So 361, the 3 was useless. 61 raised to 36, right? Which is 36 into 60 into 1 raised to 35 plus 1 raised to 36 simply. Check. Are we okay till here? Then, and this you'll now have to do it, right? Or it's too simple. So you can apply techniques even now, like 19 is 20 minus 1 or 60 is 60 plus 1. But it's very simple to do it directly as well. Right? So 19 ones are 19, 1 carried over, right? And 19 six are 114. So is this where this is ending with a 5, 9? If there are no calculation mistakes in my work, then 20 minus 1 should give you the same answer. Now try and do it with that method. Is it matching? Oh. Let's do this now. 20 minus 1 raised to 73. So again, in the last two terms that we have, it is 73, right? Dot 20 dot minus 1 raised to 72 plus simply minus 1 raised to 73, right? Now this becomes plus, right? So your, what is the last term now? 2 into 3, 6, correct? 60. Can you confirm that? Minus 1, which gives me 59 again. And have we not tamed 9 as well now? Check. Any doubt here? We've tamed 9 as well now. 5, 3, 7, even though we are going to do it. You see, many times the binomial theorem can help you get across the sum, even if you don't remember all these myriad rules and different rules. Just keep trying to apply the binomial theorem intelligently. And for me, nothing like making it somehow end with 0 and then otherwise 1, because then it makes it very simple to crack the last digit or the last two digits, so that's how you want to keep trying to break it. Like, how we're going to handle 3. One of the ways is 3 squared is 9, and 9 is easy because it's 10 minus 1, or 3 to the power 481, and all of those numbers can also then be handled because they'll end up with a 1, and you can get your answer. Check. Hope this made sense for you. Short, sweet session on the NMAT and the OMATs and the remainders with 9 and the last two digits and stuff that we want to do. Hope you all had a good time. Good night. See you tomorrow.